The CCD can be replaced by a CMOS sensor, and this is the heart of the camera. On the back view we have LCD, which is the main component, which led to the rapid replacement of these digital cameras by their analog counterparts will get replaced by their digital counterparts. Because in analog cameras we have to wait till the image is finally processed and we get the final outcome to see what image we have captured. But in digital cameras we have the immediate feedback, what the final image is going to look like. Here is the most interesting part which we will be using, is the digital camera's image processing pipeline. The light originating from the original scene goes through a number of different complicated paths to finally give us the image which we store on our camera in the form of JPEG or TIFF image. First of all, the light passes through a set of lenses, the purpose being to focus the light on the imaging sensor. Then this light passes through a set of filters, main of which is anti-aliasing filter and infrared blocking filter. Then the light reaches the imaging sensor. In between the imaging sensor and the filters is CFA or color filter array. I will explain in a minute why we need this CFA. Then finally our CCD or CMOS gives us voltage values corresponding to the light intensity falling on it. We need to digitize this voltage value and finally store them in user specified format, say TIFF or JPEG. Now for imaging sensor we can have either CCD or CMOS. Those are the main sensors used, and CCD cover the major portion of the market presently because of their good quality. Now this CFA. Our imaging sensors, CCD as well as CMOS, both are, so to speak, colorblind, in the sense that they just count the photons which are falling on them. They don't have any way to discriminate which wavelength of the light they are interacting with. So if we have just one CCD or CMOS sensor, then we will be producing basically a gray level image. We don't have colors in it. So to get the colors, one possible solution looks like we can have 3 CCD or CMOS sensors, and each one, the incoming light will be broken into 3 parts corresponding to R, G and B, and each one will capture one of the colors. But this solution is not practically feasible, because the imaging sensor is the most expensive part of the camera, and we can't afford to have 3 sensors to make the camera still on the consumer end. So what is the solution? The solution is offered by color filter array. Color filter array is basically a set of filters where each pixel is now assigned a particular color. What we do is we filter the light reaching the particular pixel so that every pixel is just measuring one of the colors, say red, green or blue. We can have different kinds of CFA patterns. We can have in the YMCG space or we can have in the RGB space. The RGB one is the most common, and then we have at every pixel only one color information. So to get the other 2 colors, we need to go through some kind of interpolation algorithms which will give us the values of other 2 colors at every pixel. And there are a lot of different CFA interpolation algorithms existing, and depending on that there are certain image forensic techniques which tend to use these differences in the cameras to figure out which camera has generated a particular image. Our focus is with the noise. As with any other sensing device, these CCD or CMOS sensors have also some noise incorporated with them. Here in this model, the Xij is the value of the ijth pixel of the original scene which we want to capture, and neta ij is the photo response non-uniformity noise. That is a kind of multiplication factor which comes here because even if we are capturing, say, uniformly lit scene, we are not going to have the pixel values which are exactly same over all the CCD, because due to the manufacturing defects intrinsic to the process of manufacturing, different pixels in the CCD have different responsivity. Then we have an additive noise epsilon ij, which corresponds to the FPN, fixed pattern noise. The source of fixed pattern noise is basically dark currents. By dark currents we mean that even if we have no light falling on the imaging sensor, we are still getting some output, and that corresponds to the dark current noise. So, and then this f represents a nonlinear function which incorporates all other operations done that we mentioned earlier, gamma correction and color, other things like that. So, the main noise of the CCD which we are concerned with are fixed pattern noise and photoresponse non-uniformity, PRNU. These two components are fairly constant over the frames. That is, even if we are using the same camera to capture different images, these two components will be having a constant values, and together they are sometimes called pattern noise, with which we are concerned. So we wish to utilize this pattern noise to differentiate between different cameras. Let's see how. Now the problem, if we see here, before we get the final image, we have a non-linear function operating on the captured values and the noise. And in most of the consumer-end cameras and even scientific cameras, we don't have access to the raw data that is before those non-linear operations. They just store the final JPEG or TIFF image. So it's not possible to recover that pattern noise using some kind of process like flat fielding, where we capture basically uniformly lit scene and then solve that equation to get back our pattern noise. So we have to find out a way around it. What people are doing is, if the average number of images captured from a single source, we will be left with mostly the pattern noise, which is constant with all the frames. To speed up this process, we can first do the denoising of the image. What we'll do, basically we'll use certain kind of denoising filters, and then we'll subtract this denoised image from the original image. That will give us the noise corresponding to that image. And if we average these noises, we will be essentially eliminating the random components and enhancing the fixed component of the noise. That way, by averaging the estimated pattern noise across many known images which are coming from the same source, we will have the pattern noise corresponding to that source. Then these patterns can be used in the classification step to classify an incoming image whose source is unknown. See the block diagram of the same process. We have a set of images which are coming from the same camera, and we denoise it and extract the noise corresponding to those images, and then we average all these noise patterns to get the camera reference pattern. The assumption in the solution of this problem is that whatever the image which we are going to test on is coming from one of the cameras on which we have already trained our classifier. So we have already a set of camera patterns, and we have an unknown image coming to us. We'll do the noise extraction on it, and then we'll correlate this, find the correlation of this noise pattern of the unknown image with all the existing camera patterns. And finally we will decide on the basis of which camera is giving us the maximum correlation value. That way we will pick up the camera among one of them who has generated the image. Here is our experimental setup. Yeah.
Have you guys done that then already? Has this been done?
Yeah, this has been done. Not only us, but some people outside also are trying similar techniques to do the camera detection.
How does, if you apply steganography, how does that affect the image? Have you checked that out? Or have you?
Yeah, that question we can deal at the end, because there are a lot of things which you can do. The basic simplest thing you can do to for this technique not to work as it is, as in done in watermarking, you can desynchronize the noise pattern. So you can extract the same noise pattern and shift it by 1 pixel here or there, or you can remove the noise pattern. That way you can easily avoid detection by this kind of approach. Simple.